Hello everybody. In the last class, we ended up discussing on generalized coordinates. So let me just remind you that a little bit. We have n particles moving in usual 3D Euclidean space. So for this, I needed 3n variables to describe the motion of the system. And then we said that along with this, I have n constraints. Constraints are the restriction in the motion of the system. And they usually, we model them in Newtonian mechanics by evoking constraint forces. But nevertheless, their restriction in the motion of the system, the number of constraints we denoted as k. So let me do that. So if I want to now describe the motion of this dynamical system, the maximum number of independent variable rather, required is small n, which is 3n minus k, because in k directions the motion is restricted, so I don't need to consider the motions along those directions. In general, it can move in 3n, so 3n minus k is the maximum number of independent variable required to describe the dynamics of the system. This we call the degrees of freedom. And then we said from the 3n original coordinates, now I can define coordinates, let us call them q1 to qn, and this is what we call the generalized coordinates. And there are certain transformation properties between the x1, y1, z1 up to xn, yn, zn. So from this original set of 3 capital N coordinates, I get this n coordinates, and that's just a coordinate transformation. And we discussed what are the rules that this coordinate transformations, what are the properties of this coordinate transformation in the end of the last class. So this is what we did in the at the end of the last class. Today we will go a little bit further. We have defined a new set of coordinates based on the maximum independent variable required to describe the motion of the system. Now we'll try to associate a space with this coordinate. Okay, and this space is known as the configuration space. And just to discuss this mostly, I talked to you earlier what we mean by a space, what are the metrics, and what are other properties like the topological properties of a space. So let us now discuss how do I define the configuration space. So let me give you the definition first, and then we will elaborate on that. So we consider a geometrical construct or a space n dimension. This is something that you already have studied, is the same dimensionality as the number of generalized coordinates. That is not good enough to have coordinates associated with a space, and we have seen that the same space can be seen from many different coordinates. So what is more required is to give it a geometry, give it a metric. We say that we consider a space of n dimension where the generalized coordinates are taken as rectangular. So rectangular means Cartesian, essentially, axis. Sounds very vague. So let us try to understand what it means. So let's go by examples. Examples are always very good means of understanding things. So let us consider the case of a circle. Okay. So why am I describing a curve? Because if you remember that the metric tells you what is the distance along a curve in a space. So we had 2 points which are infinitesimally separated, and the distance between these 2 points, if we call dr, metric tells you what is dr in terms of x, y, z, the coordinate system that you choose, and the space you live in. So let us consider the case of a circle, and this circle is being looked at in a 2D polar coordinate. So 2D polar coordinate, if you remember, the coordinates are rho and phi. Circle is the case where rho is constant. If I choose now these as my generalized coordinates, and to avoid confusions, give me names. So I call q1 is as rho and q2 as phi. And what am I supposed to do? Using this prescription given here, the generalized coordinates are taken as rectangular axis of the configuration space. So I have to plot rho here, which is nothing but q1, and phi here, which is nothing but q2. So how will a circle look like here? So it's rho equals to constant, which means q1 equals rho 0. That's just a line at q1 equals rho 0. So you see immediately the curves looks different. A circle doesn't look like a circle, and that essentially is telling you that this coordinate, the generalized coordinate, as we have given an example here, has a different geometrical property or metric property than the original set of coordinates. You can write down the metric that has information about that geometrical property. And why this new geometrical property is being imposed on the configuration space? Well, if you think of it a little bit, I initially had these 3n variables required to specify the system, and they got restricted to this small n number of variables by the constraints, k constraints. So it must be this k constraints which is imposing the geometrical properties in the configuration space. And that's exactly what happens. All the information of the constraints gets hidden in the metric of the configuration space. And we can actually see that. Remember, we wrote down the kinetic energy. The kinetic energy in the 3D Cartesian is given by I equals 1 to n, and then you have xi dot square plus yi dot square plus zi dot square, and I forgot to put the all important mass. We had capital Xi. It should be defined as root over of mi and then xi. Then only you can write the kinetic energy as, if I have a system which is not acted by any force, no constraints, then these xi's are my generalized coordinates. Because if there is no constraint, we had n equals the number of independent degrees of freedom was equals 3n minus the number of constraints. If there is no constraints, k is 0. So xi can be treated as the generalized coordinates. And this we wrote in terms of dr square, dr whole square by dt whole square. And dr square is nothing but, if you remember, it's gij dqi dqj. So you see immediately that the presence of the metric in the kinetic energy, and you know that if it's a completely free system, there is no force acting on it, all its dynamical information is there in the kinetic energy. And here in the form of the generalized coordinate, we kind of see that it depends on the metric. So in this case, this is a very special case where I don't have any constraint, but we will see examples later where if we have constraints where the kinetic energy hides all the information in terms of when it is written in the generalized coordinates in terms of the metric in the generalized coordinate. Okay, so now that we have written down this kinetic energy, let us look at it a little more further. So what are these xi's now? These xi's are, remember, my generalized coordinates. So they are like n different axes, right? 3n different axes, and this, in this case 3n is equals to small n. So in this form of kinetic energy, we have coordinates of a point which are given by x1 to x small n. In this case, n small n is equals 3n, because for this particular example k equals to 0. In general, obviously there can be non-zero k. So this is the coordinates I can level like q1 to qn. Now think of the configuration space now. If I level all these coordinates, give them a given value, this corresponds to a point in the configuration space. Now that is interesting because remember, initially how were we describing the motion of the system? We had this underlying 3D Cartesian coordinates, and if I have n particles moving in this 3D Cartesian coordinates, then for one particle, and let's say they are moving at constant speed, so there is no force, so they will move in straight lines. So different particles, I will get different straight lines. Assume that these are straight lines, though they are not probably very well drawn straight lines. Okay, and if I consider any instant of the system, this particle which is moving in that particular straight line may be here, this particle may be here, this particle may be here, this particle may be, okay, so that particle I have already considered, so this particle may be here. So you see, the system is given by 4 points here. So there are 4 points here, and all 4 points I have to specify state of the system. On the other hand, if I try to do the same thing in the configuration space, which I cannot draw now, because if I have 4 particles, I will have in this example I will have 3 into 4, which is 12 axes, which I probably will not be able to draw. But schematically, it will correspond to only one point. That's this point in the configuration space. So let me. This is a schematic drawing again. So this is configuration space. So Qi, one of the I, say like Qi prime. So this is a point in the configuration space which corresponds to all these 4 points. So this is called a C point, C for configuration. And what about the trajectory? Well, the trajectory of the system, say this is moving this way, this is moving this way, this is moving this way, this is moving this way. The trajectory of the system, not an individual particle, is given by the motion of all these points, which means in terms of the configuration space, Q1, how does it move as a function of time? Qn, how does it move as a function of time? So all these I have to tell you, all these n time dependent function, I have to tell you to describe the configuration of the system. Describe the motion of the system. Here, motion of the system is motion of 4 points. What will happen here? So for every instant of time, I will get another point. So if the time instant is nearby, I will get another point, another point, another point, another point, and you see that it will move like this. Okay. And deliberately, I did not draw a straight line here corresponds to the motion of this system, just because in case I have a constant force, because of the geometry of the configuration space, it will not remain a straight line. That I have already demonstrated to you, that a circle in the configuration space doesn't look like a circle. So your homework is to figure out what about a straight line, 2D polar. So this is a question for you. So if I have a 2D polar coordinate system, first you have to write down the straight line in the 2D polar coordinate system, and then have to figure out how does it look in the configuration space, where you take your horizontal axis as rho 0 and the vertical axis as horizontal axis as rho and the vertical axis as phi. Okay, so we realize many things. First of all, we defined a space where space we call the configuration space, which has n dimension, the number of independent variable, maximum number of independent variable, or degrees of freedom of the dynamical system. And we said that we'll consider a generalized coordinate and take the generalized coordinates as rectangular axis of a space that will induce a geometry on the space. We'll call this the configuration space. Then we realized that in terms of the configuration space, the entire system at a given instant of time is just given by one point in the configuration space, which we call the C point, and the further evolution of the system is given by a curve, which we can call the C curve, and this is essentially the C curve. If I tell you how does all the coordinates varies with time, that will give you C curve. Now there is a very important point. The point is, okay, so and you realize that if this C curve is given by this, it's essentially the trajectory of the particle in the configuration space. So I can relate the original Euclidean space with the configuration space. So that transformation we have done, and this transformation preserves certain properties and does not preserve certain properties. It turns out that this preserves topological properties. What does it doesn't preserve? Well, it's obvious that it doesn't preserve the metric properties. And that's what is changing, right? As you go from one space to the other space, the metric properties are changing. So it doesn't preserve the metric properties, but it preserves the topological properties. And this is, we are talking about the transformation from the Euclidean space, where we are writing down the original 3n coordinates, to the configuration space, which is n dimensional. So this is 3-dimensional, this is n dimensional. What other type of transformation the configuration space can have? As we said, that there can be different types of generalized coordinates that I can choose, and the configuration space could be constructed in terms of all these generalized coordinates. Given a particular problem or particular system, obviously for different systems, you can have completely different generalized coordinates and configuration space, and they will have no connection to each other, no necessary connection to each other. But imagine that I am, for a given problem, given system, I am defining a new set of generalized coordinates, and I call this a qi prime, and the functional relationship between qi prime and the original qi are this. And there is, you can imagine that there are n such functions, because both of them has to have the n dimension, because they are generalized coordinates of the same problem. Now this type of transformation between two sets of generalized coordinates describing the same problem need to again follow certain properties, and we'll see why. First, it should be a finite transformation, means if I have q as finite for a given point, c point, for the other c point it should not go to infinity, the other c point cannot go to infinity, it should be single valued. So one c point in one of the configuration space will map to one c point in the other configuration space, continuous. So if I have a curve, that should map to a curve, differentiable. And this is related to the finiteness, that at least one Jacobian element is non-zero. So let us, to understand the last point, we looked at similar transformation properties, exactly similar transformation properties, when we went from the original 3n coordinates to the n generalized coordinates. And there also we mentioned this point, but we did not had a look explicitly. So let us look at it explicitly for this particular case. So if I consider, say, the first case, so dq1 prime, I consider an infinitesimal transformation. So what will be dq1 prime? Well, I can just expand this in Taylor series. So this will dq1 prime by del q1 dq1 plus da 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 del q1 prime del qn. Now these are the Jacobian element. Jacobian is essentially given by this quantity, and you can see that this is the case where I equals to 1, j equals to 1. This is the case where I equals to 1 and j equals to n, right? And I will have these n cross n, these numbers, I can write them in a matrix form. So Jacobian matrix is that, you can take the determinant of that, it's called the Jacobian. Why do I need one of the Jacobian to be non-zero? Well, you see, if assume all of them 0, which means whatever I put in the right hand side, whatever I put in here, always in the all the left hand side elements will be 0. Whatever type of transformation I do, so what are these quantities? So it's basically what you are doing is, I am saying that I am going from q1, I am going to q1 prime, and q1 prime is nothing but q1, or let me put this as a vector. This can be doubted by the mathematicians, but what does it mean? It means essentially that I have all the q's, so I will not even write q1, I will write just q. So q, which is essentially q1 to qn, is changed to q1 prime, q prime, which is q1 prime to qn prime, and in this case we are saying that it is just an infinitesimal change. Okay, and these infinitesimals, these are essentially dq1 to dqn. Now for the first case, where I get dq1 prime, that is given by this, and then you can write n of them and you will get all the transform. Now we said that what happens if all these Jacobian elements 0? If all the Jacobian elements 0, then whatever I put in this dq, the left hand side is always 0. Now, if you think of it in a vector form, again I am drawing schematically, say this is my q. Say in one case I choose dq this way, so I go to this point, this is my dq, such that this is my q prime. Another case I choose, so this is a different transformation where I choose dq this way, so this is my dq, this is my q prime, right? Now we agreed that it has the transformation has to be single valued, means that if I do this transformation, if I go there, if I do a different transformation, I should go somewhere else. But if I have all the Jacobian 0, then I always stay there. It doesn't move because whatever the values of these dq's are, because the Jacobians are 0, these things will be 0. That is telling us that we cannot have all the Jacobian elements 0. At least one has to be non-zero such that you move the point a little bit. So now what is this doing? What is this type of transformation doing is nothing but moving one point in the configuration space to another point in the configuration space. Because of this, these are called point transformations. But what we were doing when we talked about transformations of the space is the following. So let us assume that we have only 3 generalized coordinates because it's easier to draw. And then we said that we have done a coordinate transformation of the generalized coordinates, or we have chosen a different set of generalized coordinates. Whatever you wish, they are the same thing. I have gone there. But you see, in this case, if I have a point, C point, I will denote that C point here. When I do the coordinate transformation, see that the generalized coordinates are chosen as the Cartesian axis here. The generalized coordinates are also chosen as Cartesian axis here. So when I do the point transformation, what happens is that this point appears to be somewhere there, neighborhood of this point. Now, these two generalized coordinates, these two constructs, these two drawings, both has the same Cartesian axis. So I can actually make them fall on top of each other. So if I make them fall on top of each other, then what will happen? So say this is one set and this is the other set. The axis will be exactly top of each other because that's my definition, the Cartesian axis. In one case the point was here, in the other case the point will appear here. And now if you imagine, then if I keep on doing this infinitesimal coordinate transformation and putting them in the same on top of each other, I will essentially see this point moving around and it will make a C curve. So we can say that the configuration space, this is happening just because all of the cases I have the coordinate axis as the Cartesian axis maps into itself, means that they can be put in on top of each other in a point transformation. And remember that if I do many such transformation, I will get a C curve. So a C curve can give instance, different instance of time of the dynamical system that we have already discussed. The C curve gives different instance of the time of the same dynamical system. So point transformation essentially moves the system from one point in time to another point in time. So that is very important. And infinitesimal point transformation, in general also it is true, but I am writing infinitesimal explicitly, moves a dynamical system. I can say in time. So it's giving the time evolution of the dynamical. Now this I am keeping in quote because you should think about it a little more, and it's not a complete statement. One needs to revisit it later. But that is all that we wanted to talk about in configuration space, about configuration space. And you see that it's not a very simple concept. Let me go back and revise a little bit. We defined it as the as an n-dimensional space where the generalized coordinates are taken as a rectangular axis, and we saw that it can have very weird geometry. In the case where a particle is constrained, it will impose certain geometry on it. If the particle is constrained to move in a circular motion, then you see that it will have a trajectory which looks like a straight line in the configuration space. And I asked you to calculate the trajectory of a straight line in 2D polar when I consider rho and theta 0 are the two axes of the configuration space. And what else did we look at? You look at the transformation properties from x to q. We mentioned that if I have many particles which are given by many points in the original Euclidean space, now corresponds to only one point in the configuration space, which you call the C point. And if I have each coordinates moving with time along the trajectory of a particle, that corresponds to a single trajectory in the configuration space, which we call the C curve, instead of having n trajectories in the Cartesian or Euclidean space. We discussed that when you go from Euclidean to the configuration space, then it preserves the topological properties, but it doesn't preserve the metric properties. And then we discussed the transformation of coordinates in the configuration space. We talked about infinitesimal coordinate transformations, and we realized that the Jacobian, one of the Jacobian element has to be non-zero. Otherwise, a point will, many points will map to a single point, which is not allowed for the transformations in the configuration space, or uh, yeah, in the configuration space. And this type of transformations we called point transformation. Further, we said that for all these infinitesimal transformations, series of infinitesimal transformations, if I keep on keeping them on or stacking them on each other, what I will see is the point moving in the configuration space, and it will form a curve which we call the C curve. If these transformations are are given by the dynamics of the system, this C curve then essentially is the trajectory of the system. So an infinitesimal point transformation moves the dynamical system in the configuration space. It moves it in time. So this is what we discussed so far. Okay. See, it may sound a little artificial to you to introduce such a complicated concept of configuration space, but let me give you a little insight about of it, why it was it is so important to understand what a configuration space is. The application, the real application of this is really outside our syllabus, but when we talk about all these mechanics, we are still limited to the inertial reference systems. Remember, that is what was given in Newton's first law. However, now we know, for last 100 years, we know how to work in all, any reference system, be it non-inertial, inertial, whatever it is. And the theory for that came by Einstein. It's called the theory of general relativity. And that relativity part is, it's called general relativity because it talks about the motion relative to any reference system. That's why general. And it turns out that what Newton missed, that how to work with non-inertial reference system, is nothing but choosing the right configuration space. If I choose the right configuration space, and I cannot explain to you what do I mean by choosing right configuration space, but the problem of doing physics in a general reference system is just the problem of choosing the right configuration space. And that is what was done in general relativity. And when that understanding came, then you realize that this configuration space is the core of the physics. So you should write down your physics equations in the configuration space, not in the usual Euclidean space. Once you have done that, it can be shown, and we could have had that discussion, but I thought that it would be more complicated for this course. If I write down the equation in the configuration space, it doesn't care about which coordinate system you are writing it from. Um, it can be seen a little bit here because once you choose a problem, then you see I can put the different instance of the system on top of each other and I get this nice trajectory. And you ask the question which reference system, which configuration space this trajectory is? Well, it's a trajectory in all configuration space because all of them are equivalent. All that you do once you have chosen a problem, well, all that you do by changing the configuration space or doing a transformation on the configuration space, doing a point transformation, is to go from one point to the other in the same space. Okay, that's may sound complicated, and it is complicated, so I don't want to discuss it further. If you still want to talk about it, we can discuss it in the discussion section a little bit. So let us move on. And the next two topics we want to discuss is a little bit off from the course, because we really don't have this in this course syllabus. But still, I want to continue with this idea of configuration space, because it's very powerful, and how it is used in defining the generalized force, and then the the principle of virtual work, and D'Alembert's principle. But I understand that you also have gone through this already, so I will go through this part a little bit faster. Okay. So let us consider application of external forces. So what are the external forces? So let's say that the external forces are so what are they? Well, if I choose the ith particle, I'm writing this in 3D Euclidean, and remember there will be a total of 3n such components given, has to be given. Some of them can be 0, but still you have to tell that it is 0. And for the ith particle, there is a force along x acting on the particle, which is fxi. There is a force along y acting on the particle, fyi. And there is a force along z acting on the particle, fzi. And they can obviously in the some of them can be in the opposite direction, whatever you choose, but it's just one example. So these are the forces. Okay. So now we have seen, in case of no external forces, all that we have is the kinetic energy function. And it's a scalar. We seek for another function. So what is the scalar function that describes external forces? The scalar function that describes the external forces is called the work function. We call, say, like, let's write this as delta W. It's a scalar function, remember. We'll see why that is important. And this, we know that force times displacement is the work done, and from that the work function is constructed. So 1 for x, 1 for y, 1 for z. And this is for the ith particle I have written down. Obviously, you sum over all the particles. So that is the scalar function which has information about all the forces. We have done a coordinate transformation from this. So this is written in 3D Euclidean space and Cartesian coordinates. Now from there, let us move to the generalized coordinates. If I do that, then say I write down delta omega can be written as I equals 1 to now small n, because there is n generalized coordinates. So I claim that I can write it this way, the same delta omega. See, this is the beauty of the fact that it's a scalar. Because it's a scalar, whatever coordinate transformation I do, the scalar doesn't change in coordinate transformation. This is the definition of a scalar. So these two quantities are exactly the same. What I do is that I define the work function again as dqi times some fi, and this fi I call the generalized force. So these, what are these fi? Now you realize that how many components does this have? This has n components. Original thing had 3n components. So these are 3n forces. So we had written down here. So these are 3n forces. Where goes, how do I reduce from 3n to n? Where goes the number of constraints, the components along the constraints? Well, those are the constraint forces, and they doesn't appear in the generalized force. So generalized force are only, this is only external forces. And why do I go with only the external forces? Why don't I need the constraint forces? I don't need the constraint forces because you remember the information of the constraint forces is already there in the kinetic energy function. So if I already have them already in the kinetic energy function, I don't need them here anymore. So now we have not said what is the relation of this f's with the fx, etc. But let us ask the question, what is the property of delta W? So delta W have the property that it's a differential of first order. What does it mean? It means small change in dqi gives small change in delta W. That is what you mean by differential of first order. If it's differential of second order, say delta W is proportional to dq square, then small change of dq will give very small change of delta W if you wish. Now it is written, so it's, I have not written this, so delta W not necessarily have the form d, say some u, where u is a function of q1 to qn. So it's not necessarily have this form. So it's tentative to think that it has this form, because see, du I can always write as del u del q1 dq1 da 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 del u del qn dqn. I can write it this way always. But what I'm claiming is it is not necessary that delta W can be written in this form. If I can write it in this form, then what happens is this del U del Q1 is essentially your F1, right? If I compare this, this is delta W, and remember that we defined the generalized forces. So if I consider the coefficients of dq1 from the both sides, this is essentially this. And this is only true if delta W have a differential form of a function. We call this u. If f1 or fi can be written as del u del qi, then we can define a potential function. If you wish potential energy function, I will call it potential function. And you know from our usual mechanics, that potential is minus gradient of potential is force. So we define this potential function v, which is minus, the way we have defined u, it is just minus u. Okay. And what happens if I do that? So we already know, I will not like to prove it to you here. We already know that the kinetic energy plus the potential energy is a constant for this type of systems, where I can define the force in terms of the gradient of the potential. That is exactly what we have done here. More interestingly, a single function, a single work function u, or you can equivalently v, so they are just negative of each other, can be used to get all the forces. So all the forces comes out of a single function. That's very powerful. This function you can see is very powerful. Once I know this function, I know all the forces. So these type of forces are called monogenic forces, and they are conservative forces. That I have not proved to you. As I said, that I will go a little faster, but this will be true. Okay. Other hand, so remember that what is the work function? Remember we defined this work, infinitesimal work done, or work function delta W. So, but it is not necessary that delta W will always be written in terms of du. But if it can be done, then I have monogenic forces, conservative forces, and from that single function u, I can generate all those forces. Okay, all those generalized forces, if you wish. On the other hand, I can have, say, one case can be like this, that u I get, which is a function of, which means now my delta W, if I write it in terms of u, if it is du, then it's given by, okay, so del u del q1 del u del qn plus del u del t. I have dq1 dqn, and it is clear that it does not have the form, so this is not equivalent to having the form of summation over I. So if this I have assumed, then this cannot be true, right? So that is not the case of a monogenic force. That is the case where obviously I don't have a conservative force, so my potential depends on time, right? So these are called non-monogemic forces, and you can actually work them out at each time separately, because at each time at each instant of time this term goes to 0, and then you can match these two sides. But that doesn't serve the purpose very well, because you want to know the trajectory of the system, and for each time if you want to do the things separately, then you really don't go up to the trajectory. Okay, so this is what I wanted to, so this is enough for today actually. So this is what I wanted to convey to you today. Next day we will see how do you use the idea of the configuration space and the generalized coordinate to describe the dynamics of a system. And I'm not going to go through the virtual displacements, principle of virtual work, and the D'Alembert's principles one by one. I will kind of accumulate them separate together in a kind of geometric picture, which will tell you that what is the approach that one is taking in this way of describing the system. And once that is done, we will go to a more stronger way of doing variational principles, which not only works with monogenic forces but also works with non-monogenic forces. You see that there is a restriction here. The Euler-Lagrange prescription has problem with forces which are not monogenic, but we'll go to describe dynamical systems using Hamilton's principle, which works with both monogenic and non-monogenic forces. Thank you. See you next time.